Welcome to Science to Sleep By. Tonight, as you lie back and let the weight of the day slowly drift away, I invite you to take a journey into the quiet vastness above our world. We are going to travel, not with rockets or machines, but with thought, with imagination, and with wonder. The question before us is simple, yet endlessly profound. Where does space stop? For as long as we've gazed at the night sky, we've looked for edges, for boundaries, for the place where something ends and something else begins. We draw borders on maps, we build fences around land, we measure miles and mark horizons. But when we lift our eyes to the stars, the question becomes less certain. Does space have a wall, a limit, a final frontier, or is it an ocean without shores? This is not a lecture, but a gentle voyage, a story to ease your mind and slow your breathing, as science becomes not just facts, but a lullaby of perspective. As you listen, your thoughts expand outward, like ripples across a calm pond, until you, too, feel part of something far larger, something infinite, something that never stops. From the earliest days of human thought, we have been creatures who search for limits. We want to know where a river begins and where it flows to the sea. We mark the edge of forests, the top of mountains, the end of a road. When we first discovered the shape of the earth, round and immense, we wanted to measure it, to know how far it stretched, to define it with numbers. Boundaries have always given us comfort, a way of wrapping the unknown into something the mind can hold. But space, the great dark above, does not offer its edges so easily. It resists definition, slipping through the fingers of certainty. The question of where space stops becomes not just scientific, but philosophical, even poetic. When you look up at the night sky, the sense of distance is overwhelming. Stars seem to sit on a black velvet dome, close enough to touch, but you know that they are not close at all. They are impossibly far, their light, traveling for years, centuries, even millennia to reach your eyes. And still, you can't help but feel that there must be an edge somewhere. If everything we know has a beginning and an ending, does not space itself follow the same rule? That instinct, so deeply human, has guided generations of scientists, philosophers, and dreamers, all trying to answer a question that feels simple, yet unlocks some of the deepest truths of the cosmos. Our ancestors tried to answer this in their own way. Ancient cultures often imagined a solid boundary above the sky, a dome, a roof, sometimes even a crystalline shell holding the stars in place. The heavens were thought to be literal ceilings, protecting the earth below. For them, space stopped at that imagined barrier. Beyond it were the realms of gods, the lands of spirits, or mysteries too dangerous to name. These early visions, though scientifically incorrect, reveal something important: the need to draw a line, to decide that somewhere there must be a final wall. It is almost as if the human mind rebels against the idea of infinity, because infinity does not fit easily into the containers of thought. As time passed and science grew, those barriers began to fade. The invention of the telescope shattered the idea of a nearby ceiling. The stars were not fixed lights painted onto a dome, but suns, scattered across vast gulfs of emptiness. The moon was not a glowing disk, but a rocky world with mountains and craters. Planets that once seemed like wandering stars were revealed as globes circling the sun. With every discovery, the boundary of space was pushed farther outward, receding beyond reach. What was once thought to stop at the clouds was revealed to stretch far beyond sight, and even now, we find no edge waiting for us. This search for boundaries is not just cultural or scientific, it is deeply personal. When you stand at the edge of an ocean and look out over the waves, you feel both wonder and a small tug of fear. The horizon suggests an ending, but you know the water continues on, beyond the curve of the earth. Space is like that ocean, except it has no shore, no beach to return to, no place where water meets land. It rolls outward endlessly. But because we are human, we keep trying to draw imaginary lines. We ask, where does Earth's atmosphere end? Where does the solar system stop? Where does our galaxy's influence fade into the black between the stars? Each answer is a kind of map, a comfort, though each one is temporary, for with new knowledge, the boundaries shift again. Scientists often remind us that space is not like the neat categories of a map, with clear-cut edges. Instead, it is a gradient, a slow fading from one realm into another. The atmosphere does not abruptly stop. It thins, becoming less and less dense, until air is no longer air, until a human body could no longer breathe. The gravitational pull of Earth does not cut off like a cliff. It weakens, stretching outward forever, always exerting at least some tug, though smaller and smaller as you move away. Even the solar system has no hard edge. Instead, it has regions, the orbits of planets, the scattered rocks of the asteroid belt, the icy bodies of the Kuiper belt, the distant Oort cloud, and beyond that, the faint pushback of the solar wind against the winds of other stars. Each of these markers is a kind of boundary, but none of them is final. This is where the question grows richer. If space does not stop in the way a wall stops a traveler, then perhaps the better question is how we, as observers, define the limits. Maybe, where space stops is not a matter of what exists, but of how we measure, how we choose to mark the passage from one realm to another. Space, in this sense, becomes less of a physical structure with edges, and more of a continuum, a spectrum of transitions. To call one layer the end, and another the beginning, is as much a human choice as it is a natural truth. There is something soothing about this realization. Imagine floating upward, rising through the atmosphere. The air around you becomes thin, the blue fades to black, the curve of the Earth becomes visible. You cross the K'Rm line, that human-chosen boundary, and the world of space begins. But even then, you are not in an absolute new realm. The pull of Earth is still strong. Satellites and the International Space Station still orbit within this transitional zone. Higher still, you move beyond into orbits of the Moon, past the reach of human footprints, and outward toward the space between planets. At no point is there a sudden line. Instead, you drift, seamlessly, from one layer into the next. Boundaries become gentle, gradual, almost like the blending colors of a sunset rather than the sharp border of a wall. For a mind at rest, this thought is deeply calming. If space has no final edge, then there is no cliff to tumble from, no sharp drop into nothingness. Instead, there is a vast, unbroken expanse that stretches smoothly away, like a great ocean of quiet. It is the ultimate reminder that endings and beginnings are often illusions, and that nature prefers transitions, gradients, and continuums. The human need for hard lines, for fences and walls, is a matter of psychology, not of physics. The universe itself is under no obligation to match our desire for final edges. When scientists describe the cosmos, they often use terms like observable universe. This phrase reminds us that our own knowledge is bounded, not by space itself, but by the limits of light and time. We can only see as far as light has traveled since the beginning of the universe. Beyond that horizon, there may be infinite more, but we cannot reach it, not yet. The edge, in this case, is not an actual stopping point of space, but a limit of vision. It is the cosmic equivalent of standing on a beach and looking to the horizon, knowing the ocean continues on, but hidden by distance. In this way, the boundaries of space are less like physical barriers and more like the edges of perception. The question of boundaries also carries with it a humbling message. If we cannot find a true end to space, then perhaps we must rethink our place in it. We are not standing at the center of a finite box, looking toward its walls. We are suspended inside an endless expanse, a universe that grows larger with every discovery. Instead of feeling lost, we might let this awareness bring peace. The lack of edges means there is no cage, no restriction, only openness. The sky above your head does not stop. It is a pathway without end. To drift through it, even in thought, is to surrender to something far greater than ourselves, something without limits. Something that cannot be boxed in or cut off by lines. When we begin to ask where space starts, the most natural place to begin is with the sky itself, the thin, protective blanket of air that surrounds our world. The atmosphere is at once invisible and vital, something we rarely think about, but depend upon every second of our lives. Every breath you take is made possible because of this fragile film of gases, wrapped around Earth like a skin. It shields us, warms us, filters sunlight, and makes life possible. And yet, like all things, it has a limit. The air does not stretch forever. At some point, it thins to nothing, and the silence of space begins. But finding that boundary is not as simple as pointing to a single line. The atmosphere fades gradually, like twilight blending into night, leaving us to ask, at what point have we truly left Earth behind? The first thing to understand is that Earth's atmosphere is not uniform. It is structured in layers, each one with its own character, temperature, and density. Closest to the ground is the troposphere, where we live and breathe. This is the layer of weather, the stage for clouds, storms, and winds. It stretches roughly 7 to 12 miles above the surface, depending on where you are in the world. In the tropics, it rises higher, polar regions, lower. Above the troposphere lies the stratosphere, home of the ozone layer that filters the sun's ultraviolet rays, and then the mesosphere, where meteors burn up in bright streaks of fire across the night sky. Higher still is the thermosphere, an ethereal zone where the northern and southern lights shimmer and satellites begin their endless dance. And beyond, fading into nothing, is the exosphere, the outermost veil, where atoms of hydrogen and helium drift away into space. Each of these layers is real, defined by changes in temperature and composition, yet none of them ends abruptly. There is no hard shell, no wall of air that suddenly stops. Instead, the molecules grow fewer and fewer, the density drops, and the familiar comfort of atmosphere dissolves into the blackness of space. It is a transition, a cliff, and it forces us to ask, at what point do we stop calling it atmosphere and start calling it space? For scientists and organizations that need practical definitions, one common answer is the Kármán line. Named after the Hungarian-American engineer Theodor von Kármán, this line is placed at 62 miles, or about 100 kilometers, above Earth's surface. Why this particular altitude? Because it is the point where the atmosphere becomes so thin that traditional airplanes can no longer generate enough lift to stay aloft. To travel higher than this, one must rely on the physics of orbital motion, not the lift of wings. For this reason, the Kármán line has become the internationally recognized boundary of space. It is a convenient marker, a symbolic frontier, the place where astronaut wings are awarded, the place where the atmosphere gives way to the cosmos. But the truth, as always in science, is more nuanced. Some organizations, including NASA and the US Air Force, define space as beginning slightly lower, at 50 miles above the surface. This is the point where the atmosphere is already so thin that a vehicle behaves more like a spacecraft than an airplane. In fact, many astronauts have earned their wings after flying above this altitude, even if they did not quite cross the Kármán line. This debate highlights the difficulty of pinning down a boundary in something that fades so gradually. Like the colors of dawn, there is no precise instant when night becomes day. If you could rise slowly through these layers, you would notice the atmosphere changing around you. At first, the air would cool as you climbed out of the troposphere, then warm again in the stratosphere as ozone absorbed the sun's ultraviolet light. Higher still, the temperature would drop once more, then rise dramatically in the thermosphere, where solar radiation excites the thin particles of gas. But you would also notice something else: the thinning. Your lungs would begin to strain for oxygen, and without protection, your blood would boil away in the low pressure. The sky would darken from blue to deep indigo to black. Stars, invisible in the daylight below, would pierce the heavens even as the sun shone nearby. Slowly, the comfort of air would vanish, and you would find yourself in an environment that no longer feels like Earth. Yet even at hundreds of miles above the planet, there are still traces of atmosphere. The International Space Station, orbiting at about 250 miles up, is not truly beyond all air. It still encounters wisps of molecules, thin enough to be negligible, but enough to cause drag over long periods of time. Satellites in low Earth orbit eventually feel this drag and must boost themselves to stay aloft. If left alone, they spiral slowly downward, burning up in the upper atmosphere. This invisible resistance reminds us that the atmosphere does not have a sharp edge. Instead, it bleeds outward, fainter and fainter, until it simply blends with the emptiness. The exosphere, the last faint whisper of Earth's air, stretches thousands of miles into space. Here, individual atoms can drift for hours, even days, before colliding with another. In some cases, they escape entirely, slipping away into the solar wind, never to return. If one asked where the atmosphere truly stops, one could point to this region. But then again, its influence is so diffuse, so ghost-like, that it hardly feels like atmosphere at all. It is more like a memory, a fading echo of Earth's breath, dissolving into the void. What is striking, as you reflect on this, is just how thin the atmosphere is compared to the planet itself. Earth's radius is nearly 4,000 miles, yet all the breathable air, all the sky we know, is contained in just a handful of miles at the surface. If Earth were the size of a classroom globe, the atmosphere would be thinner than a layer of varnish on its surface. This fragility is humbling. We live beneath a veil so delicate that, from space, it looks like a pale blue halo shimmering against the black. Astronauts often speak of the overview effect, that profound shift in perspective when they see how paper-thin this life-giving shell truly is. To them, Earth appears not as a vast and limitless world, but as a small, fragile oasis suspended in a great sea of nothingness. For those on the ground, the sky seems endless. Clouds stretch to the horizon, airplanes climb for hours into the heights, storms tower into the stratosphere. But from above, it is a narrow skin, a tenuous cover that can be crossed in minutes by a rocket. To imagine leaving it is both exhilarating and terrifying. Beyond it lies the great silence, the vacuum where human bodies cannot survive unaided, where warmth and breath vanish, where Earth becomes only a curved blue marble in the distance. And yet, despite its fragility, the atmosphere is astonishingly powerful. It shields us from meteors, burning them into streaks of light before they can strike the surface. It filters dangerous radiation, scatters sunlight into the soft blue glow that fills our days, and holds warmth through the greenhouse effect, making the planet habitable. Without it, Earth would be barren and frozen, like the moon. With it, Earth is alive, green, and filled with voices. The atmosphere is the great boundary keeper, the mediator between Earth and space, the stage on which all life depends. As we look upward and wonder where space begins, we are really asking about the reach of this shield. Where does Earth's presence fade, and where does the universe begin to assert itself? The answer is not simple, but layered, nuanced, and gradual. And in that gradualness lies a kind of beauty. Instead of a wall, we find a gradient. Instead of a cliff, a slope. The atmosphere reminds us that in nature, beginnings and endings often blur. That transitions are gentler than our minds prefer to imagine after passing through the thinning atmosphere, through the troposphere, the stratosphere, the mesosphere, and finally beyond the thermosphere. We arrive at a realm that humanity has learned to inhabit, at least in fleeting ways. This is the domain of low Earth orbit, often called LEO, a region of silent pathways circling just above the planet, where machines and people alike trace arcs across the sky. Here, Earth is still overwhelmingly present. Its gravity holds everything fast. Its magnetic field still shelters. Its blue surface still dominates the view. And yet, here too, there is something profoundly different. Something that feels distinctly like space. It is weightlessness, silence, and an uninterrupted horizon curving away in every direction. Low Earth orbit begins at altitudes of about 100 miles above the surface and extends upward to around 1,200 miles. Within this range, a vast collection of satellites and spacecraft circle Earth at tremendous speeds. To remain in orbit, an object must travel quickly enough that as it falls toward the Earth, the planet's surface curves away beneath it. This constant freefall is what creates the sensation of weightlessness. Astronauts inside the International Space Station are not beyond Earth's gravity. In fact, gravity there is still about 90% as strong as it is at the surface. They feel weightless because they are falling perpetually. their fall perfectly matched to the curve of Earth, never striking the ground. This zone, though still well within Earth's gravitational grip, is where human beings have lived and worked beyond the planet. Since the dawn of the space age, when Sputnik first traced its lonely path in 1957, low Earth orbit has become a bustling neighborhood of machines. Weather satellites circle here, watching clouds and storms. Communication satellites connect continents. Earth-observing spacecraft monitor forests, oceans, and cities, giving us an almost living portrait of our world. Each satellite follows its path with clockwork precision, circling the Earth in as little as 90 minutes. From the ground, they appear as pinpoints of light gliding silently overhead, a reminder that even now, humanity has placed its footprint in the sky. Perhaps the most iconic presence in low Earth orbit is the International Space Station, orbiting at an altitude of about 250 miles. It is a remarkable achievement of engineering and cooperation. Larger than a football field, it moves silently across the sky at 17,500 miles per hour, circling Earth once every hour and a half. Inside, astronauts float through modules filled with experiments, testing how the human body adapts to long-term weightlessness, how plants grow in microgravity, and how materials behave in space. To them, the view outside the window is breathtaking, Earth sprawling endlessly beneath. The blues of oceans, the greens and browns of continents, the whites of swirling clouds, all framed against the pure black of space. From this vantage point, they witness 16 sunrises and sunsets every day. A rhythm of light and shadow unlike anything on the ground. Life in low Earth orbit is both wondrous and challenging. Every movement must be careful, as momentum carries you farther than expected. Sleep comes while floating, strapped lightly into a bag, as there is no up or down. Meals must be prepared in ways that prevent food from drifting away. Even water, released from a straw, forms shimmering spheres that drift like jewels in the air. The human body itself undergoes changes here. Muscles weaken without constant use. Bones lose calcium. Fluids shift upward, making the face puffy and the legs thin. Astronauts exercise for hours each day just to keep their bodies strong enough for the return to gravity. These adaptations remind us that Earth is our natural home, and that living in orbit, while possible, is an ongoing challenge. But low Earth orbit is not just about astronauts. It is the realm of an invisible infrastructure that supports modern life. GPS satellites, though technically in higher orbits, are part of the system that allows us to navigate with phones and cars. Communication satellites relay signals for television, internet, and phone calls. Earth-observing satellites track weather patterns, measure ocean temperatures, and monitor deforestation. Without this constant watch from above, our understanding of the planet would be far less complete. Low Earth orbit has become a mirror, reflecting back to us images and data that deepen our awareness of Earth's changing systems. There is also a more sobering aspect to this region. Alongside the active satellites and stations, there are countless pieces of debris, fragments of old rockets, defunct satellites, and even tiny flecks of paint. Traveling at orbital speeds, even the smallest piece of debris can be destructive. Space agencies around the world monitor this orbital junkyard carefully, predicting collisions and sometimes moving spacecraft to avoid them. It is a reminder that our reach into space carries responsibility. Just as we must care for oceans and forests, so too must we care for the delicate shell of space around our planet. For it is quickly becoming crowded. Despite these challenges, low Earth orbit holds a unique position in our exploration of the cosmos. It is close enough to Earth that communication is nearly instantaneous, yet far enough to reveal the full curvature of the globe. It is a laboratory, a proving ground, and a stepping stone. Every spacecraft that has ventured farther to the Moon, to Mars, to the outer planets has passed through this region first. It is the threshold, the gateway to the wider universe. Imagine, for a moment, standing on the surface of Earth at night and watching the sky. A pinpoint of light moves steadily across the darkness. It is not a star, not an airplane, but a spacecraft in low Earth orbit. Perhaps it is the International Space Station, carrying people, their lives unfolding in weightlessness. Perhaps it is a satellite, silently transmitting weather data, or relaying a phone call. In that moment, you feel the connection between Earth and space, between the ground beneath your feet and the machines that circle far above. The boundary between atmosphere and orbit becomes less of a divide and more of a continuum, a reminder that the world is larger and more interconnected than it seems. Low Earth orbit is not the final boundary of space, nor is it the farthest we can go, but it is the region we have learned to inhabit, a place where humans have taken their first steps off the planet. It is familiar enough to be within reach, yet alien enough to challenge every assumption about daily life. It is a place where Earth is always present, filling every window, reminding astronauts of home. And yet, it is also a place where the blackness of space begins, where the silence grows deeper, and where the dream of venturing farther stirs with every orbit as we drift outward from the realm of satellites and the quiet pathways of low Earth orbit. The next great marker in our journey is the moon. It hangs in the night sky as a pale companion, familiar and constant, yet profoundly distant when measured in human terms. The moon is more than a light in the darkness, more than a backdrop for poetry and myth. It is a world in its own right, scarred by ancient impacts, silent and airless, locked forever in a dance with Earth. And it is also a boundary of sorts, a signpost in the invisible web of gravity that stretches outward from our planet, binding both worlds together. The distance to the moon is staggering when we pause to think of it. On average, it lies about 238,855 miles away from Earth. That is nearly 10 times the circumference of the planet itself. If you could drive a car straight upward at highway speeds, it would take more than 4 months to reach it. And yet, on the scale of the cosmos, the moon is astonishingly close. A beam of light travels from Earth to the moon in just over a second. For astronauts in the Apollo era, the journey by rocket took about 3 days. This duality, distant by human standards, but close in cosmic terms, makes the moon a kind of bridge, linking our world to the wider solar system. The moon's relationship with Earth is governed by gravity. Gravity is the invisible tether that keeps the moon in orbit, preventing it from drifting away into space. But gravity is not a force that switches on or off at some boundary. It fades gradually with distance, weaker and weaker, but never quite gone. Earth's gravity pulls not only on the moon but on everything within its reach, from small satellites to faint particles of dust. The moon, though massive in human terms, is still a smaller partner in this gravitational embrace, always falling around Earth, always locked in orbit. This gravitational bond has shaped both worlds profoundly. It is responsible for the tides that rise and fall on our shores, the rhythmic breathing of the oceans that has guided life on Earth for eons. Twice each day, the seas respond to the moon's pull, swelling and retreating in a silent dialogue between planet and satellite. On the moon's surface, Earth's gravity is still felt as a subtle tug. If you were standing there, the horizon would be strange and close, the sky utterly black, and the Earth would hang unmoving above you, always in the same place, a vast blue and white globe suspended in silence. This is because the moon is tidally locked, rotating on its axis at the same rate it orbits Earth, always showing the same face to us. This synchronous dance is a reminder of the delicate balance created by gravity's slow but relentless work. When humans first traveled to the moon, the magnitude of this relationship became clear. Leaving Earth orbit, Apollo spacecraft had to escape the immediate pull of Earth's gravity while still remaining within the Earth-Moon system. As they coasted outward, there was a point where Earth's pull and the Moon's pull became comparable, a kind of invisible frontier called the Hill Sphere, the region in which Earth's gravitational influence dominates. For Earth, this sphere extends more than 1,000,000 miles into space, encompassing not only the moon, but much farther beyond. Inside this region, Earth's gravity is stronger than that of the sun or any other body, meaning that objects tend to orbit Earth rather than being pulled away. The moon, then, is not at the edge of Earth's reach, but rather a milestone within it, a companion bound firmly by the gravity of home. yet the story of the moon and Earth is not static. The moon is slowly drifting away, receding from Earth by about 1.5 inches each year, over the course of billions of years. This adds up to vast changes. Long ago, the moon was much closer, looming larger in the sky, raising enormous tides that churned Earth's young oceans. In the distant future, it will be farther away, its pole weaker, its presence smaller. This slow retreat is driven by the tidal forces themselves, as the energy of Earth's rotation is transferred into the moon's orbit. It is a reminder that even seemingly eternal relationships are in motion, evolving on timescales far longer than human lifetimes. For astronauts who walked upon the moon, the sense of standing at the boundary between Earth and space was overwhelming. From the lunar surface, Earth appeared vast, a glowing marble floating in a black sky. The contrast was stark. The moon was gray, dusty, silent, without air or weather, while Earth shimmered with oceans, clouds, and life. Looking back at Earth from the moon was a revelation, a perspective never before experienced by human eyes. It was from this vantage point that the famous Earthrise photograph was taken during Apollo 8, showing the fragile blue planet rising above the lunar horizon. This single image changed the way humanity thought about itself, reminding us that we are small, united, and adrift together in space. Low Earth orbit may feel like the threshold of space, but the moon represents something more profound. It is the first body beyond Earth that humans have visited, the first place where footprints remain untouched by wind or rain, preserved in silence for millennia. It is a symbol of exploration, but also a marker of Earth's influence, held tightly by gravity yet undeniably separate, a world apart. For many, the moon embodies both the nearness of space and its vastness, a place that can be reached, yet still so far from the safety of home. As you imagine the journey there, you might picture the spacecraft coasting through the emptiness, leaving behind the faint traces of atmosphere, passing beyond the orbits of satellites, heading steadily outward. The Earth would shrink behind you, a sphere floating in the darkness. The silence would deepen. After days of travel, the moon would grow larger, its craters and shadows coming into focus, until at last you would slip into its orbit, captured by its gravity, bound within the shared gravitational field of Earth and its satellite. In that moment, you would feel both how far you had come and how tightly Earth still held you. The moon is not the farthest reach of Earth's gravity, not the end of its influence, but it is the most visible companion, the most enduring partner in Earth's cosmic story. It is a reminder that even as we drift outward into the solar system, the pull of home extends far, shaping orbits, guiding tides, and weaving an invisible connection between worlds as we move beyond the moon and continue our journey outward. We enter the realm of the solar system itself, a sprawling neighborhood shaped by the pull of the sun. Here, Earth is just one among many worlds, all circling a star that has burned for nearly 5 billion years. The solar system is at once familiar and mysterious, mapped by science, yet still hiding secrets in its farthest reaches. And just as we once asked where Earth's atmosphere stops, we now ask, where does the solar system end? But the answer, like so many boundaries in space, is not a single line, but a series of invisible transitions, each one marking a new layer of distance, influence, and identity. The solar system begins, of course, at the sun itself, a blazing sphere of hydrogen and helium, fusing atoms in its core to release unimaginable energy. Everything else orbits this central star, held in place by its immense gravity. Closest to the sun are the rocky planets, Mercury, Venus, Earth, and Mars. These are the inner worlds, small in size compared to the giants, but each unique, each a story of geology and atmosphere. Beyond Mars, the asteroid belt forms a kind of transitional region, filled with countless rocky bodies, some as small as pebbles, others large enough to be considered dwarf planets. Beyond that lie the gas and ice giants Jupiter, Saturn, Uranus, and Neptune, massive spheres with rings and moons, each of them like miniature solar systems in their own right. But even Neptune, farthest of the traditional planets, does not mark the end of the solar system. Beyond its orbit lies the Kuiper Belt, a region of icy remnants, leftovers from the formation of the planets. Here we find Pluto, Eris, Haumea, and Makemake, among many others, small worlds with frozen surfaces and distant suns. The Kuiper Belt stretches outward like a vast ring, extending billions of miles from the sun. To travel here would be to enter a realm where sunlight is weak and dim, more like a pale glow than the bright warmth we know on Earth. Still farther lies the Oort cloud, a theoretical shell of icy bodies that may surround the solar system like a distant halo. It has never been directly observed, but its existence is inferred from the long-period comets that occasionally sweep inward from the depths of space. If it exists as scientists believe, the Oort cloud may extend halfway to the next star, trillions of miles away. It is perhaps the farthest boundary of the sun's gravitational influence, the region where the star's pull finally yields to that of other stars and the galaxy itself. But the solar system's boundaries are not only gravitational, they are also shaped by the sun's energy in another form, the solar wind. This stream of charged particles flows outward in all directions, creating a vast bubble known as the heliosphere. Within this bubble, the sun's particles dominate. Beyond it, the particles of interstellar space prevail. The edge of this bubble is called the heliopause, and it represents another invisible frontier, one that spacecraft like Voyager 1 and Voyager 2 have crossed. For them, passing through the heliopause was like stepping out of a familiar neighborhood and into the open wilderness between stars. It is not the end of the solar system's gravity, but it is the end of the sun's direct influence in particle winds. And so it serves as yet another kind of boundary. What becomes clear, when we think of these layers, is that the solar system does not have a single edge, but many. There is the boundary defined by the farthest planet, Neptune. There is the boundary defined by the Kuiper Belt, where icy bodies drift in shadow. There is the boundary defined by the Oort cloud, vast and hypothetical, stretching far beyond imagination. And there is the boundary of the heliopause, where the solar wind gives way to the winds of other stars. Each of these answers the question in a different way, depending on how we define end, just as the atmosphere faded gradually into space. So, too, does the solar system fade into the galaxy. To picture this, imagine drifting outward on a quiet journey. First, you pass the orbit of Mars, where the red desert world orbits cold and still. Beyond it, you enter the realm of the asteroid belt, where fragments of stone and metal circle endlessly, reminders of a planet that never formed. Then you reach Jupiter, immense and storm-filled, its moons like worlds themselves. Saturn follows, with its rings of ice and dust glowing like jewels in the sunlight. Farther still are Uranus and Neptune, pale and distant, their atmospheres filled with methane that gives them their blue hues. Here, sunlight has grown weak, the warmth of the sun no stronger than a winter twilight. As you move outward, the Kuiper Belt greets you, a vast and icy plain. Pluto drifts here, with its mountains of frozen nitrogen and plains of methane ice. Its surface is sculpted by faint sunlight and distant winds, a place so far that days last as long as weeks on Earth. Beyond Pluto, the Kuiper Belt continues, its small, frozen worlds circling in silence. To stand on one of them would be to see the sun as only the brightest star in the sky, no longer a blazing presence but a small, pale beacon. And beyond the Kuiper Belt lies the imagined Oort cloud, a spherical shell of icy bodies scattered across trillions of miles. If you could drift into that region, you might find yourself surrounded by frozen comets, drifting almost endlessly, waiting for some gravitational nudge to send them inward toward the sun. It is a realm of deep cold and silence, so far that Earth is less than a memory. This may be the true edge of the solar system, where the sun's gravitational hold fades into the background of the Milky Way. Meanwhile, the heliopause is another kind of edge, one not defined by distance to planets or comets, but by the reach of the sun's wind. Here, the solar particles slow and press against the interstellar medium, creating a kind of frontier, like the edge of a bubble. Voyager 1 crossed this threshold in 2012, becoming the first human-made object to enter interstellar space. Yet even there, Earth's sun is still the gravitational center of its orbit, still the dominant presence in the background. The heliopause is less an end and more a transition, a shift from one realm of influence to another. Thinking of the solar system's boundaries is both humbling and soothing. There is no wall, no sudden stop. Only gradual transitions. Each one farther, each one more diffuse. The solar system fades outward into the galaxy, just as the atmosphere fades outward into space. Every boundary is invisible. Every edge an illusion of perspective. It is a reminder that in the cosmos, endings are rarely abrupt. Instead, they are soft, blending one realm into the next. Like colors merging on a horizon. As we float in thought through these layers, we come to see the solar system not as a closed box with firm edges, but as a living, breathing system that stretches outward without a sharp conclusion. Earth, the moon, the planets, the belts, the clouds, the heliosphere, all are parts of a continuum, a gradient of influence reaching far into the dark. The sun, from where we stand on Earth, is a steady light in the sky, rising and setting with dependable rhythm. But in truth, the sun is not a quiet, fixed beacon. It is a dynamic star, a roiling furnace of plasma and energy, constantly releasing streams of particles into space. These particles, mostly electrons and protons, flow outward in every direction, creating what scientists call the solar wind. The solar wind is invisible to our eyes, yet it surrounds us, filling the solar system like an ever-present tide. It does not move like a gentle breeze on Earth, but rushes outward at hundreds of miles per second, carrying the sun's influence far beyond the planets. Over billions of years, this flow has shaped a kind of invisible bubble around the solar system, a vast protective shell known as the heliosphere. To imagine the heliosphere, think of the sun sitting at the center of a great glowing lantern. From its surface, waves of charged particles stream outward, moving beyond Mercury, Venus, Earth, and Mars, rushing past Jupiter and Saturn, flowing around Uranus and Neptune, and continuing in beyond Pluto and the Kuiper belt. The solar wind does not stop where the planets end. Instead, it pushes farther and farther outward, until at last it reaches a point where the pressure of particles from other stars pushes back. This balance point, where the sun's wind yields to the wind of the galaxy, is what we call the boundary of the heliosphere. The heliosphere is enormous, far larger than the planetary part of the solar system itself. From Earth to the sun is about 93 million miles, a distance we call 1 astronomical unit. The heliosphere stretches out at least 100 astronomical units in every direction, and possibly much farther. That means the sun's protective bubble is at least 100 times wider than the distance from Earth to the sun, and still may only be a fraction of its true size. Within this bubble, the solar wind shapes the environment of space. It guides charged particles, influences cosmic rays, and protects the planets from much of the radiation that fills the galaxy. Without it, Earth and its neighbors would be far more vulnerable to the harsh interstellar environment. Yet the heliosphere is not a solid structure. It is not a wall, not something you could see or touch. It is more like the wake of a boat moving through water, an invisible field of pressure created by the flow of particles. The boundary is soft, shifting, changing with the strength of the solar wind. When the sun is more active, the bubble expands. When it is quieter, the bubble contracts. This means the heliosphere is alive in its own way, pulsing with the rhythms of the star that creates it. The solar wind itself begins at the sun's outer atmosphere, the corona. Temperatures there rise to millions of degrees, so high that atoms are stripped of their electrons, creating plasma. The sun's magnetic fields guide and accelerate this plasma, hurling it outward into space. Near Earth, we feel the solar wind, not as particles against our skin, but as its effects in the magnetosphere and atmosphere. When solar storms send especially strong gusts of wind, they can disturb satellites, disrupt communications, and even cause power grids to falter. But they also bring beauty, lighting up the skies in auroras, curtains of green and red that shimmer at the poles. These displays remind us that we are connected to the sun, not just by light and heat, but by streams of energy that flow constantly between star and planet. As the solar wind travels farther from the sun, it thins out, but it does not vanish. At first, its particles move at supersonic speeds, faster than the speed of sound in the plasma itself. But eventually, as they push against the gas and dust of the interstellar medium, they slow down. This creates a region called the termination shock, a kind of boundary where the solar wind begins to change character. Beyond the termination shock lies the heliosheath, a turbulent region where the slowed solar wind interacts with the surrounding interstellar medium. Finally, at the farthest edge, lies the heliopause, the true border where the sun's influence gives way to the galaxy beyond. Crossing the heliopause is a profound threshold. It is the point at which the sun's wind no longer dominates. Beyond it lies interstellar space, filled with particles, radiation, and magnetic fields from other stars. For billions of years, the heliosphere has been a shield, wrapping the solar system in its invisible embrace. But beyond its edge, we find the raw environment of the galaxy, vast and unfiltered. The boundary is not sharp, but gradual, a transition zone where one influence fades and another begins. Remarkably, humanity has already sent explorers to this threshold. The Voyager spacecraft, launched in 1977, have traveled farther than any human-made object in history. Voyager 1, in 2012, crossed the heliopause, becoming the first emissary of Earth to enter interstellar space. Its instruments recorded the change as a drop in solar particles and a rise in cosmic rays, evidence that it had left the heliosphere behind. Voyager 2 followed in 2018, confirming what Voyager 1 had found. These small spacecraft, each no larger than a car, are now drifting through the galaxy, carrying with them the story of their makers. Yet even they are still under the pull of the sun's gravity, orbiting it in vast arcs that will last millions of years. The heliosphere was their home for decades of travel, and beyond it, they now taste the space between stars. The shape of the heliosphere has long been a mystery. For years, scientists pictured it as a comet-like bubble, rounded at the front where the solar wind pushes into the galaxy, and stretched into a tail behind. But more recent data suggests the heliosphere may be more rounded, more like a sphere than a comet. It is a reminder that even something so vast, spanning hundreds of times the distance from Earth to the Sun, is still difficult for us to measure with certainty. The importance of the heliosphere cannot be overstated. By shielding the planets from much of the galaxy's radiation, it creates a safer environment for life. Cosmic rays, high-energy particles from distant stars and supernova, can be damaging to living cells. The heliosphere reduces their intensity within the solar system, allowing Earth to sustain life as we know it. Without this shield, our planet's atmosphere might look very different, and our world might not be the same home it has been for billions of years. To imagine yourself moving through the heliosphere is to picture a journey without visible signs, without markers or borders. You would drift through a space that seems empty, yet all around you are streams of particles flowing outward from the sun. At first, the solar wind is strong, dense enough to be measured easily. But as you move farther away, the particles spread out, fewer and fewer per cubic inch, until the wind becomes thin and faint. Then you would encounter the termination shock, where the supersonic flow slows abruptly, a kind of invisible ripple in the stream. Beyond that, the heliosheath would surround you, a turbulent, chaotic zone where the wind struggles against the interstellar medium. At last, after billions of miles, you would reach the heliopause. There, the outward pressure of the solar wind meets the inward pressure of the galaxy's particles, and balance is struck. To step beyond is to enter a new environment, one not shaped by our sun, but by the combined voices of countless stars. The heliosphere is a gentle reminder that boundaries in space are not walls but transitions. They are not lines you can see, but regions where one influence fades and another begins. Just as the atmosphere fades into space, and just as the solar system fades into the galaxy, the heliosphere fades into the interstellar medium. It is an in-between place, both a shield and a bridge, both a home and a frontier, and it stretches around us every moment, whether we think of it or not, holding back the wider universe, even as it whispers of the vastness that lies beyond the vast bubble of the heliosphere. Where the solar wind meets its match against the pressure of the galaxy, lies the realm known as the interstellar medium. This is the true space between stars, the vast ocean in which every solar system floats. Unlike the emptiness we imagine when we hear the word space, the interstellar medium is not completely void. It is filled with diffuse gas, faint traces of dust, magnetic fields, and cosmic rays that travel across the galaxy. Though incredibly thin compared to Earth's air, so thin that even the best vacuum chambers on Earth are denser, it is far from nothing. It is the background environment of the Milky Way, and it is the place into which our first robotic explorers have already ventured. The interstellar medium is composed mainly of hydrogen and helium, the two simplest elements, leftovers from the earliest moments after the Big Bang. Sprinkled within are heavier elements, forged in the hearts of stars and spread outward by supernova explosions. Tiny grains of dust drift in this space as well, created by dying stars and carried by galactic winds. Magnetic fields thread through the medium, shaping the paths of charged particles and influencing the structure of the galaxy itself. Though faint and sparse, this mixture is the material from which new stars are born, gathering into clouds that collapse under gravity until fusion begins again. In this way, the interstellar medium is both the graveyard of ancient stars and the nursery of future ones. For humans, the interstellar medium was once a purely theoretical realm, something imagined by astronomers, but unreachable in practice. The distances were too vast, the scales too immense. Yet, in 1977, NASA launched two spacecraft, Voyager 1 and Voyager 2, with missions that would eventually carry them beyond the heliosphere and into interstellar space. These spacecraft were designed first to explore the planets, to make use of a rare planetary alignment that would allow them to slingshot from one world to another using gravity assists. But from the very beginning, scientists dreamed that if the spacecraft survived long enough, they might one day venture into the interstellar medium itself. The Voyager spacecraft are, in many ways, time capsules of the 1970s. They carry instruments built with technology that seems simple by modern standards, yet robust enough to last decades. They are powered by radioisotope thermoelectric generators, using the heat from decaying plutonium to produce electricity. Their antennas, wide and white, still point back toward Earth, sending faint signals that take over 20 hours to arrive. Each Voyager also carries the famous golden record, a phonograph disc coated in gold and etched with sounds, images, and messages from Earth. On it are greetings in many languages, music from cultures around the world, and images of life on our planet. The record was designed as a gift, or perhaps a message in a bottle. Should an intelligent civilization ever encounter the spacecraft millions of years from now, Voyager 1E's journey took it past Jupiter and Saturn, capturing breathtaking images and measurements of these giant planets and their moons. Voyager 2, on a different path, flew past Jupiter, Saturn, Uranus, and Neptune, becoming the only spacecraft ever to visit the latter two. Their planetary encounters revealed storms larger than Earth, moons with active volcanoes, icy worlds with mysterious surfaces, and ring systems more complex than anyone had imagined. These discoveries transformed our understanding of the outer solar system and set the stage for decades of exploration to come. But after the planetary flybys ended, both Voyagers continued their outward trek, driven not by destination, but by momentum. They became wanderers, leaving behind the familiar realm of planets and heading into the deeper dark. As Voyager 1 moved farther from the Sun, scientists watched for signs of the heliopause, the point at which the spacecraft would leave the Sun's protective bubble. This crossing was not marked by a sudden visible sign, but by changes in the particles and magnetic fields measured by its instruments. Inside the heliosphere, the spacecraft detected many particles from the solar wind. Outside it, those particles dropped sharply while cosmic rays from the galaxy increased. In 2012, scientists confirmed that Voyager 1 had crossed the heliopause, making it the first human-made object to enter interstellar space. Voyager 2 followed in 2018, providing more detailed measurements of the boundary and confirming that the sun's bubble truly does have an edge where the interstellar medium begins. What makes this so profound is not only the distance traveled, but the symbolism of the crossing. For the first time, something built by human hands had left the immediate influence of our star and touched the environment between stars. The Voyagers, still sending data decades after launch, became our eyes and ears in a realm no living being has ever visited. They revealed that the interstellar medium is not empty, but filled with structure, with subtle shifts in density and magnetic fields. They showed that cosmic rays are more intense outside the heliosphere, confirming the protective role the sun's bubble plays for planets like Earth. And yet, even now, the Voyagers remain close by galactic standards. Voyager 1 is more than 14 billion miles from Earth, but the nearest star system, Alpha Centauri, is 25 trillion miles away. At their current speeds, the Voyagers would take over 70,000 years to reach it. This means they are only a few steps out the door of the solar system, barely into the interstellar sea. And yet, in human terms, their distance is unimaginable. The signals they send back are faint whispers, requiring the largest radio dishes on Earth to detect. Their power is dwindling, and within the next decade or two, they will fall silent, becoming mute travelers adrift in the galaxy. The interstellar medium into which they travel is both harsh and serene. Temperatures are near absolute zero, yet radiation passes through it constantly. There are no landmarks, no planets, no moons. Only the faint dust of old stars and the far-off glow of the Milky Way. It is a place of loneliness, but also of connection, for every star in the galaxy shares this medium. Every planetary system embedded in the same cosmic fabric. The Voyagers, small as they are, now drift through this shared space, carrying with them the voice of Earth. To picture Voyager moving outward is to imagine a silent craft, no longer warmed by the sun, its instruments cooled by the dark, its antenna aimed forever at a pale blue dot far behind. Around it, hydrogen atoms drift like invisible fog. Magnetic fields stretch and bend, guiding cosmic rays along their lines. The sun's light, once bright, is now little more than a star among stars, indistinguishable from the thousands of others scattered across the sky. And ahead, there is no destination, only endless space, a journey that will never end. The golden record, attached to the side of each Voyager, may outlast everything else. Protected by a thin coating of gold, it is designed to survive for billions of years, longer than Earth itself may endure. Long after the spacecraft have gone silent, long after the last traces of humanity have changed or vanished, those records may still drift on, carrying the music of Bach, the sound of ocean waves, the laughter of children, and greetings in dozens of human tongues. In that sense, the Voyagers are more than machines. They are symbols of curiosity, of a species reaching beyond its home, of a quiet hope that some may find and understand. The interstellar medium, vast and quiet, will be their home for the rest of time. It is not a place we can yet visit ourselves, but through the Voyagers, we have touched it, measured it, and begun to understand it. They are our scouts, our messengers, our way of stepping into the unknown without leaving Earth. In their faint signals, in their long journeys, we hear an echo of our own longing to know what lies beyond the horizon, to ask not only where space stops, but what it means that it may never stop at all when we look upward into the night sky. Beyond the planets, beyond the faint band of the Milky Way, we are peering not just into distance, but into time itself. Each star we see is a reminder that light takes years to travel across space, and the farther we look, the farther back in time we see. Telescopes extend this vision beyond the reach of the human eye, revealing galaxies scattered across the darkness like islands of light in a boundless sea. Each galaxy is a vast collection of stars, billions or even trillions, bound together by gravity, and yet none of them are fixed in place. They are all part of something larger, something that defies our natural sense of boundaries, the universe itself, not static, but expanding. The expansion of the universe is one of the most remarkable discoveries in science. For centuries, many people imagined the cosmos as infinite, but unchanging, a grand stage on which stars and galaxies might move, but which itself remained fixed. That picture began to shift in the early 20th century, when astronomers noticed something astonishing. The galaxies around us were not standing still. They were receding, and the farther away they were, the faster they seemed to be moving. This discovery, first hinted at by Vesto Slipher's measurements of redshifts and later confirmed by Edwin Hubble's work with distant galaxies, revealed that the fabric of space itself was stretching. It was not that galaxies were flying through space like bullets, but rather that space itself was expanding, carrying the galaxies with it. To understand this expansion, imagine a balloon with tiny dots drawn on its surface. As the balloon is inflated, each dot moves away from the others, not because the dots are moving on their own, but because the surface itself is stretching. The universe works in much the same way, though it is not the surface of a balloon, but the three-dimensional fabric of space expanding in all directions. There is no central point from which it expands, no privileged place where the expansion began, only a universal stretching everywhere at once. This expansion means that the universe does not have a fixed edge, no boundary, like the walls of a room. If you were to travel in one direction forever, you would never find a barrier, no cosmic fence or wall at the end of everything. Instead, you would continue moving through space that is itself growing larger with every moment. The galaxies would continue to recede, their light growing fainter and redder as they move beyond our sight. This is why the question, where does space stop, becomes so difficult. It does not stop in the way a road ends or a coastline runs out. It continues, stretching into regions we cannot yet see, and perhaps into regions we will never see. What makes the universe even more mysterious is the discovery that its expansion is not slowing down, but speeding up. In the late 1990s, astronomers studying distant supernova found that galaxies were receding faster than expected. This suggested that some unknown force, something scientists call dark energy, is driving the acceleration. Dark energy is not understood. It is not like the ordinary matter we see, nor like the dark matter that seems to bind galaxies together. It is instead a property of space itself, an energy that pushes the universe outward, faster and faster as time goes on. If this continues indefinitely, the universe will become an ever-expanding emptiness, with galaxies rushing away from one another until they vanish from view. For us on Earth, this expansion is imperceptible on everyday scales. Our planet does not grow larger, nor does the solar system. Gravity binds these structures together, holding them against the stretching of space. Even our galaxy, the Milky Way, remains intact. But on the largest scales, across billions of light years, expansion dominates. Clusters of galaxies drift apart, and the cosmic web of matter, stretching across the universe, becomes ever more diffuse. The farther away we look, the faster the galaxies recede, until at last their light is stretched so much that it can no longer reach us. This creates a horizon, not of matter, but of visibility, a cosmic limit to how far we can see. This horizon is known as the observable universe. From Earth, we can observe light that has traveled for about 13.8 billion years, the time since the Big Bang. But because space has expanded during that time, the most distant galaxies we can see are now more than 46 billion light-years away. Beyond that distance lies the unobservable universe, regions we cannot see because their light has not yet had time to reach us. And beyond even that lies the unknown space that may continue forever, or that may curve back on itself, or that may connect to other universes entirely. The observable universe gives us a sense of scale, but it is not an edge in the true sense. If we could somehow move to one of those distant galaxies, and look outward from there, we would see another observable universe stretching just as far in all directions. Each observer in the cosmos has their own horizon, defined not by walls, but by the finite speed of light and the age of the universe. This makes space both infinite in possibility and finite in what we can perceive. The cosmic microwave background offers another glimpse into this boundlessness. It is the faint afterglow of the Big Bang, the cooled radiation left from when the universe was just 380,000 years old. It surrounds us in every direction, a soft echo of the moment when the universe first became transparent to light. By studying this radiation, scientists can trace the structure of the cosmos and measure its expansion. But even the microwave background does not represent a true boundary. It is simply the farthest we can see with light, a horizon that hides what lies beyond. As we come to the end of this quiet journey, let us return to the question that began it all. Where does space stop? The truth, as we have seen, is that space has no fixed edge, no wall, no final border. The universe is not like the land and oceans on a map, with neat boundaries to divide them. Instead, it is something far greater, a fabric that stretches in all directions, expanding endlessly, carrying galaxies and stars further apart, leaving us adrift in a cosmic sea with no shoreline. What we know, and what we do not know, blend together into a picture of both science and wonder. We can measure the observable universe, tracing light across 46 billion light-years, but we cannot say what lies beyond that horizon. We can calculate the speed of galaxies drifting apart, and we can study the afterglow of the Big Bang, but still, the ultimate fate and shape of the universe remain open mysteries. Some scientists speak of infinite space, others of a finite but unbounded cosmos, others still of parallel universes beyond our reach. And yet, despite these unknowns, the lesson remains the same: the universe does not stop. For us, lying here on Earth beneath a star-strewn sky, that realization is both humbling and comforting. We are part of something immeasurably vast, something that began nearly 14 billion years ago and will continue for billions of years to come. Every breath we take, every thought we form, happens within this boundless expanse. Space may not stop, but neither does our connection to it. We are made of the same matter, forged in ancient stars, carried along on the same expanding fabric of space, part of the same cosmic story. So, as you drift into rest, let your thoughts settle on that image, a universe without edges, stretching softly outward, with galaxies, like lanterns floating away into the dark. You are here, in this moment, safe on this small blue world, and yet also connected to that endless expanse. Space does not stop, it flows, it grows, it carries us forward, and in its quiet, unending reach, it invites us not to fear its vastness, but to find peace in knowing that we belong within it.